All right, I think we can get started. I know other people will join soon. So welcome everyone to this pre-seminar series. So today actually we have the pleasure and privilege to have among us Professor Marcelo Sanchez. So Marcelo Sanchez is professor in the Zachary Department of Civil Engineering at Texas A&M University. He obtained his first degree in civil engineering from the Universidad Nacional de San Juan in Argentina. And then he got a master's degree and a PhD degree from the Universidad Politécnica de Catalunya in Barcelona, Spain. His expertise lies in the area of advanced geomechanics with a focus on problems that involve thermal, hydraulic, mechanical, and geochemical couplings. Marcelo is actually a world-renowned expert of the multiphysics of geomaterials. His research also covers the study of the behavior on saturated soils and expansive clays. Application of his research are broad and in particular include energy geotechnics, geoenvironmental engineering, transportation geotechnics, among others. Marcelo is acting as an associate editor for various journals, actually 7 international journals, and he received multiple awards, including the George Stephenson Medal from the Institution of Civil Engineers in the United Kingdom. Professor Sanchez is also the founder and current chairman of the Technical Committee 308 on Energy Geotechnics for the International Society of Soil Mechanics and Geotechnical Engineering. And I can attest that he is the soul of many initiatives and events that occur worldwide in this scope. So with that being said, Marcelo, thank you again for being here. Today, I guess you will be talking about coupled multiphysics analysis of geoenergy problems, and we are all ears. Thank you.
Thank you, Alessandro, for the introduction, and thank you to the Department of Civil and Environmental Engineering at Northwestern University for the opportunity to present our work here. Let me share now the presentation. Now it should go.
Perfect.
You see my presentation now, right?
Perfect. Yes.
Okay. Well, the title is what Alessandro mentioned. I am going to be talking about coupled multiphysics analysis of geoengineering problems. It will be a very general talk about application of this analysis for problem that we have in geoenergy. The outline of the presentation is the following. I will start with a brief introduction to the context of the research, and then I will present very briefly the coupled thermo-hydromechanical formulation that we are using to solve problems in geoengineering. I will then mention some example of energy techniques in which we apply this formulation, and also the different challenges that we have in this area. I will focus particularly on nuclear waste disposal. I'm going to talk about a past project and a new project that we are in which we are working in this area, and finally the conclusion of this lecture. So let me start by acknowledging the colleagues, students, and sponsors that have assisted with this research during the last few years. Now, moving to the topic of the research, as you might know, the study of soil and rock under complex and extreme conditions involving mechanical, hydraulic, thermal, and chemical coupled action has received increasing attention in the last few years. And some of these actions are unprecedented. So we are really facing here new discoveries and learning more about the behavior of soil and rock. The motivation can be from different applications. Here, one of them is geoenvironmental engineering. And as you know, we use our soils and rocks to storage waste and pollutant material. And a typical example, and perhaps one of the most difficult one that we are facing now, one of the challenges that we have in our area, is the design of nuclear waste disposal. So in this kind of problem, what we are trying to do, I am saying trying because it's an unresolved problem. So nobody has solved this problem yet. There is no country in the planet that have solved the problem of safe storage of nuclear waste. So the idea is to go 500 meters or more below the ground level and construct there a system of galleries that you can see here. And this is a zoom of what we are anticipating to do there, right? So basically we have the canister that contain the very polluted nuclear waste. And generally we have an open space between the canister with the nuclear waste and the rock gallery, right? So this space is filled by what we call an engineered barrier. And we are looking at clay, compacted expansive clays to construct this barrier, right? So why we have thermohydromechanical action here? Well, this nuclear waste is a heat-emitting material, and we are looking in the design of temperature that can be between 100 and 200 Celsius. So quite high temperature. We are looking at very good quality rock, right? But we are very deep in the ground, and even in very good quality rock, we have fractures and cracks. So we are anticipating that water will eventually hydrate the barrier. And as I mentioned before, this is expansive clay. So we are expecting here swelling of this clay when it's hydrated and expansion, and we have a confined condition because of the deep that we are in the ground. We are expecting here as well quite high stresses that came from this swelling of the clay. So, and then there are also chemical action, obviously, because the chemical composition of the water in the porous space is different from the chemical composition of the water that will hydrate this barrier. So we are anticipating also cation exchange and other chemical interaction that we need to investigate to design this type of repository safe and in economical manner. We have also a number of challenges that came from energy, and just here one example that is related with enhanced geothermal system. As you might know, we have a reservoir at high temperature that can be quite deep as 200 meters or more below the ground level, and we generally use this geothermal resource to produce energy, right? So we produce water from the aquifer or steam, and we use this hot water that can be at 200 Celsius or around this value to produce energy, right? So one problem that we have is that generally when we have this geothermal resource, we don't have an aquifer. And you can see here a map of the United States, and you can see when we have very nice geothermal resource, we have what we call a dry rock. So there's no water there. There is a very low permitting material. So what we are investigating in this area is how we can induce a system of fracture in this dry rock, circulate water, and produce energy from this hot water. So the idea basically is to have two or more wells. One of them will be the injection well, in which we are planning to inject cold water or another fluid. For example, it can be liquid nitrogen that can go to a temperature as low as -196 Celsius. So it's about 400 Fahrenheit to have an idea of that. And then the thermal shock that will happen with this cold fluid is in contact with this hot rock that can be at 200 Celsius will induce a system of fracture, right? And the idea is to have an interconnected network of fracture between the injection well and the production well. So once we have this fracture network, we can circulate water through this system of network, and we can produce energy. And there are a lot of interest in this particular application nowadays in Europe and also United States. And here you have an idea of why this is that important. You can see that in 2005, United States consumption of energy was about 100 exajoules. And if we have a conservative scenario of production of energy from this resource, we can produce 2.8 times 6 exajoule, right? This is in a 2% conservative scenario. If we have more optimistic scenario, we can produce more energy than we actually need. So it's very important to study this particular problem. And here in the United States, we have tests ongoing now in Forge test site in Utah, in which the intention is to investigate how we can implement that, how we can actually produce energy from this kind of resource. So we have here again, and you can imagine, we have all of this thermo-hydromechanical action because we have this injection of this cold fluid that is inducing a change in the thermal field that is triggering the formation of fracture that is related with the mechanical problem. And then we have the flow of water to produce energy that is the hydraulic problem. So here you can see that it's very important to understand very well how this THM process work and have tools that allow us to understand the problem and to predict how this system will perform. Then we also have interest related with global warming. As you know, there are different scenarios that have been studied for what is going to happen in the future in terms of temperature patterns and precipitation pattern in our planet. This corresponds to a model that assumes medium to high CO2 production emission. And you can see that this is for the years 2017, 2100, and you can see that for at that time, we expect that all the planet will warm. This is the increase of temperature with respect to the current temperature. And you can see that the land will warm more than the ocean. And also we have higher temperature here near the tropic. When we look at in terms of precipitation, we anticipate more precipitation in the poles and more dry condition near the tropic. So this implies that we have higher temperature and higher change in relative humidity impacting our natural soils. And you know, soil tend to crack when we have this variation of relative humidity and temperature. And this will affect our natural soil and also infrastructure like levees and similar structure that we have contracted during the last few years. So we also need to investigate this problem. And as you can imagine, this is a couple thermo-hydromechanical problems. So we have several problems, and these are just some examples of problems in which we see this need to have a good understanding of these couple thermo-hydromechanical and chemical processes in soils and rocks. So this is a kind of brief description of how we see these different physics acting in a typical soil. Here you have the grains with the void space between the grains. And when we're looking at the thermal problem, the main aim is to understand how the heat will be transferred in this porous medium. When we look at the hydraulic problem is, well, how the water and gas will flow through this interconnected porous space that we have in our soils and rock. And we'll look at the stresses. Well, the mechanical problem, the main goal is to see how we transfer these stresses between the particles that we have in our porous medium and how this stress-strain behavior of the soil impact on settlements and other important aspects. But the important thing here is that these different physics are not isolated. They are interconnected. They are coupled. And here you have some example of this coupling that we need to consider in our analysis. For example, you know that the fluid density and viscosity depend on temperature. So if we have a thermo-hydromechanical problem, well, we know that the temperature will impact on the hydraulic problem. You also know that the flow of the water and gas in soils depend on permeability, and the permeability depend on porosity. So if we have change in the mechanical problem that will impact the porosity of our porous medium, we will see that this will impact directly on the hydraulic problem. We also know that the stress-strain behavior is related with effective stresses or net stresses and not total stress. So this implies that we have change in our hydraulic problem in terms of fluid pressure, liquid or gas. This will impact in our effective stress and will have an effect on the mechanical problem. And you also know that any matter when we heat will tend to expand, and if we cool down will tend to contract. So we have also here coupling between the mechanical and the thermal problem. And I can continue with this coupling because there are several of them that we should consider. But in any case, it's just to show you that how we need to consider all of these different physics all together and look at all of this interaction, because they are key to finally understand which will be the behavior of this type of system, right? Now, well, a very general slide about how we approach this kind of problem. I will try to present different examples of these different components in this presentation. As you know, in engineering, it's very important to understand the real problem, to have a good understanding of the materials, boundary conditions, step of load that we are going to have in our problem, so we can then identify which are the relevant phenomena we need to consider in the analysis. We need to write this relevant phenomena in mathematical way, because finally, you know, we are engineers and we need to solve the problem, and for that we need numerical tools, analytical tools that allow us to predict how this system is going to work under different conditions. But we also need to go to the lab, because we need to study under control condition in the lab by looking at changing temperature, pressures, or mechanical effect, how our materials react, so we can develop what we call the quantitative models of our materials. When we have this information, we should incorporate all of them in what in a numerical model. The numerical model basically allow us to incorporate all the information that we have of the problem in a single component, right? So there we need to know very well the geometry, we need to define the boundary condition, we need to define the different material, we need to define the different step of load that we have, the different thermal or hydraulic action that we are anticipating. And then what we do generally, we compare this model prediction, or this model result that we have, with tests that we have from the field, right? And then if we are confident that our model is doing well, right? We feel that the model managed to predict the main patterns of behavior that we observe in the actual problem. Well, we can use this code to do the engineering, of the problem, right? To design and so on, right? But sometimes we have problem and our model is not able to properly predict the behavior that we see in the real system. So what we need to do is to revisit our formulation. Perhaps we are missing some important components, some physics that is relevant for this particular problem, or perhaps we need to go again to the lab to see which additional tests we need to do, because there are something of the material that we are studying that we don't understand well, and we need to incorporate that in our model, then run again, compare, and see how confident we are about our model. You know, in my opinion, numerical models are always important. We always need to try to develop a model for our problem, because they allow us to synthesize all the problem in this in the model. But when you look at this kind of problem that I am talking now about, for example, nuclear waste disposal, we need to design this kind of a structure for 100,000 of years, right? So in this case, we cannot rely only on experiment. We need to have numerical tools that allow us to predict what is going to happen in the long term, right? So for that, we need to rely on some physical processes, and we also need to be sure that we have a robust model that will allow us to predict well the long-term behavior of the system. So now I will move very quickly to the formulation that we are using. Is a quite a standard formulation in which we have a system based on a basic porous system. In this case, we have our particles with a porous space, and we assume that in porous space we can have two different fluid. In this case, it can be more, obviously. In this case, it's gas and liquid. And what we are doing is basically establishing the different kind of equation. One of them is what we call the mass balance equation. And this is the example of the mass balance of water. And in this equation, what we are doing is basically looking at all the water we have in the system and looking at the water that is coming in and coming out. And basically what we are saying is that any variation of the storage of this water in the system has plus the net flux of water, when we look at the difference between the water is coming in and coming out, have to be equal to any external sink or source of water, right? So we have this mass balance equation for the different species. We are working with a multi-phase, multi-species formulation. So basically we are considering 3 different phases: solid, liquid, and gas, right? And 3 different species that is mineral, water, and air. So basically we consider that in this initial basic formulation that the solid have only 1 mineral. Obviously we can consider a more complex situation. We consider that in the liquid phase we have 2 main species: the water, the liquid water, and the air dissolved. We assume that we can have air dissolved in our liquid phase. And then as for the gas phase, we have 2 main components. One of them is the mixture of dry air. So basically we assume that we have only 2 components: this dry air and the vapor, water vapor, right? So nitrogen, oxygen, and all other gases that we have in our gas phase are considered just 1 gas, that is the dry air, plus the water that we have in the gas phase in the form of vapor, right? So this is the basic formulation. We have expanded that to consider other species and other phases, but this is the basic one. And in this formulation that was proposed by Oliveira in 1994, and then based on this equation, Codebride was developed. That is the code that we are working. We are using our analysis. We are considering 2 different type of mass balance equation. These are the mass balance of the species for the water and the air, the momentum balance for equilibrium, and the energy balance for the temperature, right? So this is I have no time to go into the details of this equation, but are quite standard mass balance equation and momentum and energy balance equation. And what we do, for each one of these equations, we assign what we call a main variable. For example, for the case of the mass balance of water is the pressure of the liquid. For the mass balance of the air is the gas pressure. For the momentum balance is the displacement field. And for the energy balance equation is the temperature, right? So this is one set of equations, and we need to add to our formulation what we call the quantitative equation and the equilibrium restriction. So in this set of equation, what we have, what we call quantitative equation, are the relations that are related with the behavior of the material, the particular material we have in our system, and basically relate dependent variables with the main variables. For example, Fourier law is used to calculate the conductive heat flux, and as you know, it depends on the thermal conductivity at the gradient of temperature. We use Darcy law for the flow problem, gas and liquid phase. Retention curve is the equation that allows us to know the saturation that we have of different species in our porous medium, liquid and gas. Fixed law is for non-advective fluxes. The mechanical model relates stresses with the strain. And then we have equation for the phase density and another equation like for the viscosity that allow us to complete this set of quantitative equations. Then we need to add 2 additional equations that are what we call the equilibrium restriction, that basically allow us to know for a given temperature and pressure condition, which is the amount of water that we have, for example, in the gas phase, and which is the amount of air that we have dissolved in the liquid phase, right? So basically, with this basic equation, we have a full formulation that we can use to solve our problems. Before going to the problems, what I'm going to do, I'm going to show very quickly some typical form of this equation, this quantitative equation that we need to determine generally from experiment in the lab. As you know, Darcy law established a relation between the velocity of the water in the soil and the permeability with the hydraulic gradient. So this is typical Darcy 1D equation that relates the velocity of the water with the soil permeability and with the hydraulic gradient. what we do in this kind of problem is we expand this, basic equation to different phases. So we use, in this case, alpha to identify the liquid or the gas, or the gas phase, and then we have a kind of generalized equation for the permeability that involves what we call the intrinsic permeability, that is a permeability that depends only on the porous structure of our porous medium, the viscosity of the fluid that is flowing through the porous medium, and the relative permeability. I'm going to explain that in a minute. And here we have, in terms of the hydraulic gradient, we express that in terms of the gradient of the pressure, liquid or gas pressure, depending if we are dealing with a liquid or gas flow, right? So K is the intrinsic permeability tensor, as I mentioned before, depend only on the porous structure of our porous medium. And then we need to incorporate, obviously, the viscosity of the fluid and other property, right? And this law here is what we call the relative permeability equation that allow us to consider that when we have this two-phase problem, so basically we have liquid and gas sharing the porous space. Well, not all the space not all the voids in the porous medium is available for the flow of gas and liquid, and we need to account, for the particular for the impact of this partial saturation on our permeability law. That basically is a coefficient between 0 and 1 that allow us to estimate which is the permeability of the gas and the liquid when we have this two-phase problem. We also need to go to the lab and to determine all of this. The relative permeability law, for example, is determined after experiment in the lab. We also need to look at how the permeability change with porosity, and here you have examples for the bentonite that we use in this nuclear waste disposal application. And you can see that the permeability that is here in this vertical axis depend strongly on the porosity of our compacted clay in this case, and we need to develop equation. This is based on Cosseni model, and this is one exponential law that allow us to basically track how the permeability will change with porosity. These are relatively basic model, right, in which we use only porosity as a variable to update our permeability. We have also developed more sophisticated model based on the porous structure, pore size distribution that we can also use if we need, right? But I am presenting here what is the basic formulation for thermohydromechanical problems. Then in terms of the thermal conductivity, well, again, we have this challenge here is the typical Fourier law, but the challenge here is that the thermal conductivity is not just depend not only one material, but on the different phases that we have in our porous medium, the solid, the liquid, and the gas. So we need to look for equation for the thermal conductivity that allow us to account for the contribution of these different phases in the global thermal conductivity of our porous medium, right? And here, as always, we need to do our experiment in the lab and to see how we can develop a thermal conductivity law that allow us to account for the effect of water saturation, porosity, and so on our Fourier equation. Then in terms of the mechanical model, this is perhaps the more complex component in this kind of system. Expansive clays are material that have a complex behavior, so it's anticipated that the modeling of this kind of material will be also quite complex. So we need to develop model that can reproduce that, and this implies that we need to develop generally what we call elastoplastic model to account for the effect of pressure, liquid and gas pressure, and temperature on the behavior of the bentonite. So here you have a typical example of one of the materials that we are considering for the case of nuclear waste disposal. This is a compacted bentonite. The density of that can be quite high, 1.7 megagram per cubic meter. And the idea is this is the rock, right? The idea is to construct a barrier, using this block around this canister that where we are going to place, you know, the canister containing the nuclear waste, right? So this is compacted material, and the basic model that we are proposing is based on CAM clay. You know, CAM clay model, the modified CAM clay model is very well known in geotechnical engineering. And what we are doing here to expand this CAM clay model to consider the effect of the suction, that the suction is the difference between the gas and the liquid pressure. We also call that capillary pressure on the mechanical behavior of the soil. What we see is that as the soil becomes more unsaturated, this elastic domain that define the ellipse of the modified CAM clay model tend to expand and grow with this increase of the capillary pressure. And we also observe that if we increase the temperature, this ellipse starts to shrink, right? So this is possible. It's possible to model that in the context of elastoplasticity, and we basically develop a model in which our stresses are updated depending on the change in strain, suction that basically involve liquid and gas pressure and temperature, right? Again, I have no time to go through all the detail of that. There are good papers there. If you are interested in this particular topic, I'll be happy to share more detail with you about that. So this is basically the formulation, and I wanted to show very quickly some of the model that we are using to quantitative model that we are using for this particular material we have here. What we need to do then is to incorporate all of these equation in a computer code. Here I am presenting code bright that is a coupled thermo, hydromechanical, and chemical code that we are using to solve this kind of problems in geological media. So what you have here are these different components that I mentioned to you before: the mechanical problem, the flow problem, the thermal problem, and also the chemical problem. And this code allows us to solve each one of these problems individually. We are only interested in the mechanical and the thermal problem, or we can also look at this interaction between these different physics to analyze these coupled thermo-hydromechanical problems. So it's a finite element code, right? It's a kind of hybrid code, and we use the Newton-Raphson method to solve the nonlinear system of equation, and we use a finite difference to solve the time evolution problem, right? We also have a program that is the GID code, also developed in Barcelona, that allow us to prepare all the information that we need to solve this kind of problem in terms of the geometry, the mesh, materials, and so on. And we can also use this code for the post-processing. So this is basically an introduction to the tool that we have been developing during several years now to analyze this kind of problem in soils and rock. Let me go now very quickly to some application in which we are interested and which we are working in Texas A&M. And I will divide this application of energy geotechnics in three main categories. One of them is this application related to energy production. So we are looking here how we, as geotechnical engineers, geomechanics, can assist to produce energy. And one typical problem is the production of oil and gas from reservoir, right? So what we do generally is try to enhance this oil and gas production by injecting fluid at high pressure in what we call the injection well. And basically this fluid that we inject, that can be water or can be CO2, will push the gas or the oil to the production well, so we can speed up the production process. So what we try to do in this case, obviously, is to try to inject the maximum pressure possible so we can produce this oil quickly. But we need to consider that we shouldn't compromise. We must not compromise the geomechanical stability of the system. And one typical problem that we have in this kind of application is the reactivation of fault. You know, we have geological fault generally that are stable. They have been there for hundreds of thousands of years. But for some, if we apply very high pressure, we might compromise the stability of this fault, and we might reactivate this fault with the the release, of oil, uncontrolled release of oil and gas through this fault. So one of problem here that we are dealing in energy technique is how we can optimize this problem of injecting at the maximum pressure possible to produce the maximum oil and gas that we can quickly, but also at the same time keeping the system safe and without inducing any fault activation or any other geomechanical problem. Hydraulic fracture, I think not all of you are well, now the animation is not working, I think. The idea here is to see how we can produce oil and gas from what we call non-conventional reservoirs. So these are shales reservoir in which have very low permeability, and we need to fracture this material in order to produce the gas that is trapped in this low porosity material. So again, if you think in this problem and the previous one, what we are doing here, we're injecting fluid at high pressure, so we are perturbating the mechanical problem to this injection at high pressure. So this is a problem also very interesting, and we are working strongly in this problem because it's critical, for in terms of energy resource that we have available for us. Then the last topic that I am going to mention very quickly is methane hydrate. It's also related with energy production, and I don't know if you know, but we have plenty amount of methane that is in the form of hydrate. This is a kind of ice structure, right? We have a structure in which methane and ice are in a crystal configuration. They are in the ground. There is a solid compound, and here you have a picture of a sediment with hydrate. These are the whiter part, right? And this hydrate is very stable, and when we have condition of high pressure and low temperature, but if we change this condition, for example, by drilling through this sediment, this hydrate dissociate. So this implies that this hydrate that is in the solid state will move will dissociate, and the methane will move to the gas phase, and the water to the liquid phase. And when this happens, we have a huge change in volume. For example, 1 cubic meter of methane hydrate can produce 178 cubic meter of gas and 0.78 cubic meter of water. So you can imagine that we have a big change if we release all of this gas during this dissociation process in our sediment. We have huge change in terms of pressure, and also is this reaction is endothermic, so we also have a strong change in temperature. So it's a very complex problem, and we're interested in this problem for different reasons. One of them is because this dissociation might trigger big instability problem in the ground. So generally we found this kind of sediment in the subsea and also in Alaska. And what we have observed is that we have this kind of event in the subsea. We affect the infrastructure that we have there. Generally, these sediments are close to production sites, so we are affecting all this infrastructure that we have in the seabed. We might affect also the offshore structure that we have there. We are also interested in this problem because we have this uncontrolled release of methane. This will contribute to this greenhouse effect, and obviously we want to prevent that. And we are also interested because these are the bad side of the hydrate, but there are also positive aspects that we have more methane in the form of hydrate than in any other form in our planet. So if we manage to propose strategies for production of methane from this kind of resource, we also have a very nice and large source of energy for us, right? So this is another important problem which we are interested in working on. Then we have the other category of problems, the one in which we basically exchange and storage energy in the ground, right? And there are different applications here, and in which basically we use the ground as a storage system for then producing, we store energy there, and when we produce this energy when we need it. I don't have time. I think I am running out of time, so I am going to escape this one, and I will move to the last one that is related with how in geotechnical engineering we deal with the waste produced in the nuclear in the energy sector, right? And I already mentioned about high-level nuclear waste disposal. That is clearly a product of the nuclear of the production of energy, or nuclear production of energy. And we also need to deal with CO2, and there is a lot of projects related with CO2 sequestration. I am not going to talk about CO2 sequestration in this particular talk, but it's another important application that in which we are working. Geotechnical engineer and geomechanical engineer are working nowadays. So I will focus a little bit on high-level nuclear waste. I will use the last minute to present this particular problem. As I mentioned before, the idea is to construct this system of galleries 500 meters or more below the ground level. This is again a kind of zoom of what we're expecting there, with the canister containing the nuclear waste, the natural rock, and the clay barrier filling the space. In the next slide, you are going to see a cut of this section here. So this is basically our nuclear waste. This is the rock, and this is the compacted bentonite. So what we are anticipating here is that we have this heat emitted from the nuclear waste that will dry out the clay around that, will shrink, and basically we have a reduction of porosity permeability near the nuclear waste. On the other hand, we have this water, this hydration that came from the external rock, and will hydrate and will induce this clay barrier to expand and to swell in the external part. So if we need to predict the time necessary for this water to hydrate the barrier and eventually arrive to the nuclear waste, right? So we need to understand very well how permeability evolve and change within this process. And this is why that is that important to understand how all of these thermo-hydromechanical process work together, right? And obviously we have, as I mentioned before, chemical effect, because we are expecting here chemical interaction between the clay that we are placing there and the rock that is hydrating the clay, right? So there are interests in this problem. As I mentioned before, we didn't solve this problem yet. We are working on that, and there are different laboratories in the United States and also in Europe. Perhaps Europe is a little bit ahead of us in terms of this kind of investigation. And here you have laboratories in different kind of rock, because we are looking at different possibilities. It might be granite, a candidate for that. It can be rock salt, or it can be a clay stone. And we have different laboratories that are in which we are running an experiment to understand how this kind of system work under real operational conditions. This is an example of the typical design. We can have either vertical borehole, in which we are going to place the canister here with the borehole, and we will fill this space with a clay barrier. We can also use horizontal drift to place the canister. I am going to talk about one particular project, that is the FEVEC project. This project was, we call that the Spanish project, was mainly funded by Spain, but also for other countries in Europe through the European Union. And in this project, we have two main experiments, one in Switzerland that is just finished 2 years ago, right, under actual scale, actual boundary conditions, actual operational condition, and a mock-up test that have the same size than the real test in Grimsel, but in this case it's in the lab, and we control the hydration, right? If you think about this problem in the rock, we don't know the amount of water that is coming to the barrier, because it's a natural system. So we wanted to control that, and this is the test that is still ongoing in Madrid, right? This is what I mentioned before, the clay barrier with the heating. We are not using nuclear waste, we're using heaters to provide the thermal load, and the maximum temperature is 100 Celsius. And this is a quite big experiment. The diameter of the barrier is 1.62 centimeter, and it's about 17 meter long, right? This is another view of the experiment. This is during the drilling of the gallery. This is the gallery just before starting the test. This is layout of the experiment with the two heater that we have in this experiment. The clay barrier is this yellow part. This is a concrete plug that isolate the heater from the rest of the gallery, in which we have all the instruments that allow us to track the evolution of the system. This vertical black line that you see here correspond to sections, instrumented section, in which we have sensors of different type. We can measure, we measure their stresses, liquid and gas pressure, relative humidity, temperature, and other variables. And these are typical location of the sensor in these different sections. We also have boreholes around the gallery. So this is the gallery, it's a concrete plug, right? And these are boreholes that were around this gallery to understand the thermal, mechanical, and hydraulic field around the gallery, right? So the experiment ran for around 18 years, and there were two main stages, starting in 1997. Then after 5 years of heating and hydration, they decide to switch off the heater one, right? And we dismantle the first part of the experiment, and then the experiment continue for another 13 years, right, until 2015, when the experiment finished, right? So this is the layout of the second part of the experiment with only one heater ongoing. So it's a very nice experiment. It's the longest one that we have had in this type of project. And here are some results of this project. This is the barrier that I mentioned to you before with this compacted block of compacted bentonite. And you can see there are some gaps between the blocks at the beginning of the experiment. This is the heater, and this is the granite, the gallery rock. And here you have the barrier 5 years after the experiment. And you can see that is more or less homogeneous. You know, all of these gaps were closed, and the barrier is mainly hydrated from the external part of it, right? So we have compared our code, and this was a kind of blind prediction because Enresa was the company in charge of this experiment, asked us to provide the simulations result before, you know, at the beginning of the project, when they start with the project. So we provide the result, and what you can see here are the comparison between the model with line and the experimental result in terms of temperature. And this is what happened in different sections. This drop of the temperature here is related with this switch off of the heater one. Okay, so these are how the temperature evolved in different points. Close to the heater, we have a high temperature that we expect, about 90, 80 degrees. Near the external, the contact with the gallery is around 40 Celsius, and in between at the central part of the gallery. So this is all the result in terms of stresses. In this case, you can see that we have an increase of stresses quite high. They were up to 5 megapascal at the end of the experiment. Also, what happened in the rock around the experiment in terms of temperature, you can see that in borehole closer to the heater, we have higher temperature we expect, but as we move away from the heater, the temperature is lower. Also, this decrease that you observe here is related with the cooling down, related with the switch off of the heater one. These are again results in terms of stresses, and again show that the model managed to predict very well the evolution of the system. These are the final results after 18 years of hydration. So this is the barrier at the beginning of the experiment, after 5 years, and after 18.3 years. These are experimental results, right, obtained from the post-mortem analysis from this test. And this is the distribution of densities and saturation. And you can see that it's more or less uniform. This implies that the barrier was more or less uniformly hydrated from the boundary. these are the same result, right? But now plotted in different manner. Here is what happened near the rock, and this is sorry, this is close to the canister, and this is as we move away, and this is near the rock. So we have a change in dry density with a very high density near the canister because of the dry, and very low density because of the expansion, swelling of the bentonite near the rock. And in terms of saturation, well, at the end of the experiment is almost fully saturated, but you know, the final part close to the heater that is still unsaturated. I think I am running out of time. Just want to show here some example of other things that we are investigating about this complex clay structure and how we can incorporate this complexity in our model to account better for some aspect that we observe in this experiment that the simple single porosity model cannot capture. So this is a topic in which we are working, how this hydration impact on this dynamic structure of the clay during hydration, and how this impact on the behavior of this material. Now we are working in a project also for the Department of Energy, looking mainly at the gas migration in this kind of system. And this is the project. We have 4 students working in this project, and we have a collaboration from Spain mainly helping us with that. The idea here is that the different metallic components of this system will oxidate, the gas pressure will increase. It can be very, very high gas pressure in the system. So we are looking at this breakthrough of the gas through the clay, and preferential pathway for the gas through this barrier system, right? We are working on that. We are now in the 2nd year of the project. We are developing new testing device for looking at this gas migration problem in bentonite, and we are also developing our code to account for this problem. This is some of the devices that we have developed in this project that allow us to test in the lab prototype of clay barrier, in which we can actually introduce a rock in our system and the clay barrier, and simulate how the gas will migrate through the contact between the clay and the rock. We also can induce a thermal field to see what happens when we change the temperature in the system. We are looking at different kind of interfaces to see how the rugosity of the wall of the rock will impact in this gas migration. And we are following different protocols to understand better how gas will migrate in this kind of system. We also anticipate that crack this bentonite might dry and might open crack. So we are looking also if this is a possible scenario, and in this case, how gas will migrate through this cracked soil. We also developed and upgraded our code to account now for this jump in the displacement, temperature, and hydraulic field, so we can account for the presence of discontinuity in our system. And we are using this code to model this problem of gas breakthrough, opening of the fracture, and gas flow, right? So let me finish with some general conclusion. I focus mainly on this problem of nuclear waste disposal, looking at how we need to develop code and experimental devices to understand how the engineered barrier and also the natural geological barrier will work and will behave and when it's subject to this change of temperature, pressure, and high stresses. The interest is looking at this thermohydromechanical phenomenon and interaction between the physics. And I also show some other cases in which we use similar tools in other problems related with energy technique. We can see that we have the potential for significant advances in this complex area, because basically we are looking at the behavior and rock under unprecedented condition of temperature, pressure, and mechanical condition. So there are good opportunity here, and especially for the students that are here in this presentation. I think we have a lot of very nice things to investigate here, and energy geotechnics is a very nice area to dedicate research and for. Thank you very much for your attention. I am sorry that I took more of the time, and I am happy to answer any question you might have.
Thank you, Marcelo. It was wonderful. Let's maybe everybody has a clap for him, physical. So thank you again. It was very comprehensive and interesting. Does anybody have any questions?
Yeah, I would like to ask a question. Sure. That was a very nice overview, broad and difficult problems, Professor Sanchez. I want to mention regarding your discussion at the beginning of hot dry rock fracturing.
Mm-hmm.
We had a big study at Northwestern in 1970s, 5 investigators and 3 from Los Alamos, and we concluded that it was not feasible. And that was followed in Japan, the same result, namely because we did not find a way to produce dense enough cracks to grow, to extract the to heat. Now, is this reviving this problem? Is there some other way?
Yes, it's reviving. In fact, you know, it's very interesting if you have the chance to go. The name is Utah Forge Site. There is DOE4 there, and you are right? There is a concern about how to develop a nice fracture of network in this kind of system. So what we are trying to do now, we are looking at system with a system of fracture, right? That we will try to enhance with new fracture, right? So this is the approach in this site, right? It's a site that
would be dense enough fracture, otherwise it would not. The widely spaced fracture would not help. Yes.
Yeah, exactly. So there is there is a lot of research here in the United States. DOE is funding that mainly, and through Utah University. And this project is very nice.
University of Utah.
Yeah. Okay. And the site is Forge, F-O-R-G-E, Forge that site, and it's ongoing. So it's ongoing, and they are in the second phase of this project. And they are looking at, you know, there are different.
You have some information on that. I would like to receive it.
Yeah, I will do. I will. But I should. Yeah, but you know, it's
another point.
UK have one observatory. Yeah. Go ahead.
Another point. You try to be comprehensive in the analysis of diffusion and transport and fracture, but one point is that osmotic pressures due to ion redistribution may have a significant role. I am not the only one to say that.
Yes,
but
sure.
Do you have any view on that? That was not part of your formulation.
No, it was not part. In fact, you know, this code was upgraded by one of my colleagues, and we keep collaborating with them, looking at this effect of osmotic suction. Yeah, osmotic suction is critical, especially, you know, in the long term. In the long term, when the gradient of pressure
in the long term, yes,
lower, you start to have all these chemical effects that play a more important role, and osmotic suction is a critical variable to study. Let's say, you know, after, you know, we have the transient of pressures, the liquid pressure, osmotic suction is the one that will play a big role there. Yeah, you are absolutely right.
Okay, thank you very much.
No problem.
Thank you, Professor Bazant. So maybe before anybody else could ask a question, I will just ask something on behalf of Professor Hambleton, who had to run because of a commitment. So he wrote in the chat that he would have asked you about the nature of CodeBright, whether it is an open source code available for use or not. If you could expand a little bit on that.
Very good question. So the CodeBright was developed in Barcelona, right? And initially, through this, you know, research on nuclear waste disposal, at the beginning was a kind of very confidential, the code, right? It was not for the public, but now is in terms of use, is open. So there's a website when you can go and you can download the code, the manual, and a number of application cases. And, you know, some of the cases that I presented here today are there, right? Perhaps simplified one, you know, for kind of instruction purpose, but, you know, but it's there. Now, in terms of modifying code bright, so having access to the source code is one thing that you need to discuss with my colleagues in Barcelona. They generally do that in terms of collaboration. So if they see that is interest in collaborating, they do that, I know. But you know, it's one thing, and this change time to time, because now I think it's mainly Sweden that is sponsoring the code, in the sense that they support a team that help, you know, with any question that you have about the code. So because you know you need a team behind the code to solve questions from the users and to update the manual and to and now I think it's Sweden the one that is assisting with that, so they might have the final word on that, right?
Okay.
But
Thank
yes,
you.
the answer is yes. The code is available, is free of use. You need a pre and post processor, and for that, GID is the best one, and GID academic, you know, have an academic version that is free, and you have the other, you know, professional version that is $1,000, I think, if you need to solve larger problem, right?
Yes.
I can send you the link to the page, to the
Thank
website.
you, Marcelo. You're an open source of information. Are there any other questions or comments, curiosities? Maybe a final one.
I would like to ask a small question.
Sure.
Yeah.
Hello. Thanks for the presentation, Professor. So how do you take into account the addition between the rock and the clay, like the bentonite clay and the rock that you have been examining? Because if different types of rocks are there, their addition with the barrier will be changing, and you will observe different phenomena there happening, right?
Yeah, so it's a very good question. We don't anticipate a lot of sharing here, right? So what we see is mainly that this clay barrier will expand and will push again the rock, right? So then we don't have this typical problem of interface in terms of stressor, right? Because we don't anticipate shear here, right? Now, why is important this interface that you mentioned? Because of preferential flow for the water and gas, right? And there, you know, there are different concepts that are being investigated. Gas is going to be generated because of the high temperature, for example, vapor will form, right? And also metal that we have there in the canister, sensor, and other thing that we are anticipating there will oxidate and will generate also gases, right? So the thing is that, and this pressure that will develop these gases can be very, very high, can be, you know, 200 megapascal or more. So, and these are, you know, I didn't do this simulation, but people that work on this kind of problem of oxidation and so on, they did that, right? So the thing, there are two ideas now. What we do, we try to contain the gas to prevent that this gas flow, or we produce at this interface a kind of rugosity to allow this gas to migrate and storage there, right? So basically you contain the gas there. So what I want to say, some people say it's better to have a kind of clean contact between the rock and the clay. Other ones say let's develop a kind of damage zone, and you know, it's the EDC, right? That is a zone that will induce damage at the contact between the rock and the clay. So we have kind of fissure and crack where the gas will migrate and will, you know, in the long term, we are talking process here about 100,000 of years, right? Will migrate and will be stored there and will not develop a high pressure. So basically you provide storage space for the gas, right? I don't know to answer your question, but the thing is that we are not worried about any mechanical effect of the interface, but we look a lot at the effect of, in terms of the hydraulic, mainly gas phenomena, how is going to work this interface.
Thank you.
Is that clear?
Yeah.
Very good.
Okay, so maybe for concision, I would end here the seminar. I guess Marcelo will have the opportunity to talk later. So again, unless there are very urgent questions, I think we can close this event. Thank you everyone for attending it. Thank you, Professor Sanchez, for the fabulous talk, and have a nice afternoon, everyone.
Thank you very much for the opportunity again. Pleasure.